We're trying to improve the accuracy of a random forest regressor model, a machine learning model that predicts house prices. The model's predictions are pretty far off from the actual house prices, as measured by the mean squared error, MSE. A high MSE means the model isn't very good at its job. Let's fix it. I'm going to explain how you can improve the model. Here are several approaches, and I'll explain how each one might help reduce that MSE. A random forest regressor uses multiple decision trees, estimators. More trees usually lead to better predictions, kind of like getting more opinions before making a decision. Each tree has a maximum depth, max_depth. A smaller depth makes the trees simpler and less likely to overfit the training data, preventing the model from being too specific to the training data and not generalizing well to new data. This parameter controls when a tree branch splits into two. A higher value makes the trees simpler, reducing overfitting, similar to reducing max_depth. This controls how many features, like house size or location, each tree considers when making a split. Reducing it introduces more randomness, which can again help to prevent overfitting by reducing reliance on any single feature. I see a high mean squared error, MSE. That means my random forest regressor model is making pretty big prediction errors when trying to guess house prices. The model isn't very accurate. Let's fix it. I need to find ways to improve my model's accuracy. I can adjust some settings, hyperparameters, to try and get better predictions. Let's examine the possible solutions. I can increase the number of trees, estimators, in my random forest. More trees usually mean better predictions because the model will be more robust. It's like getting more opinions before making a decision. I can reduce the maximum depth of each tree. If trees are too deep, they might overfit to the training data, meaning they learn the training data too well and do poorly on new data. I want to avoid that. I want a simpler, more generalized model. I can increase the minimum number of samples required to split a node. This prevents the trees from getting too detailed and overfitting to my training data. I'm aiming for a nice balance. I can reduce the number of features each tree considers at each split. Using fewer features adds randomness, which can stop my model from relying too much on any single feature and prevents overfitting, hopefully leading to more accurate predictions on new data. I'm working on making my random forest regressor model better at predicting house prices. That's the main goal. Let's get this model working like a charm. I see a high mean squared error, MSE. That means my random forest regressor isn't accurately predicting house prices. The bigger the MSE, the further off my predictions are from the actual prices. I need to improve its accuracy. I'm trying to make my random forest regressor better at predicting house prices. Random forest regressor is a powerful machine learning model using many decision trees working together. I'll tweak its settings, hyperparameters, to get better results. I can increase the number of trees, estimators, in my random forest. More trees usually lead to better predictions because the model averages more opinions. It's like getting more diverse perspectives before making a final decision. I can make the individual decision trees less complex by reducing their maximum depth, max_depth. Shorter trees are less likely to overfit to my training data, leading to better predictions on new data. It's like simplifying the decision-making process to avoid getting bogged down in minor details. I can increase the minimum number of samples required to split a node in my decision trees, min_samples_split. This makes the trees simpler and less likely to overfit. It's like requiring more evidence before making a significant decision. I can reduce the number of features considered when splitting nodes in the decision trees, max_features. This adds more randomness and avoids overfitting when some features are strongly related or irrelevant. Think of it like considering only the most important factors when making a decision, avoiding getting sidetracked by less relevant information. We're facing a problem. Our model for predicting house prices isn't very accurate. The mean squared error, MSE, a measure of how far off our predictions are, is high. That means we need to improve our model's predictions. MSE is calculated by averaging the squared differences between actual and predicted house prices. I can try increasing the number of decision trees in our random forest. More trees generally lead to better predictions because the model averages many predictions, reducing the effect of any single tree making a bad prediction. This helps improve the model's accuracy by reducing variance. Let's try limiting the depth of each decision tree in the forest. Shorter trees are simpler and less likely to overfit to our training data, meaning they'll generalize better to new houses and make more accurate predictions on unseen data. Overfitting happens when the model learns the training data too well and does poorly on new data. To prevent overfitting, I can increase the minimum number of samples required to split a node in a decision tree. By doing this, I make the trees simpler and less likely to learn the noise in the data. Simpler trees are usually better at generalizing to new data. I can limit the number of features considered when splitting nodes in each tree. This adds more randomness, which can prevent overfitting, especially if some features are strongly related or irrelevant. Using fewer features makes the trees less sensitive to noise in the data. We've identified several ways to potentially fix our high MSE problem. By testing these options, we can find the best combination of settings for our model. A high mean squared error, MSE, means my model's predictions are far from the actual house prices. It's not doing a good job of predicting the data, and I need to fix that. Think of it like this. A high MSE is like a really bad dart throw, way off the bullseye. I have a few ways to improve my model. Let's look at how changing some settings might help. Let's see what we can do here. I can add more decision trees to my random forest. More trees usually give me a better, more accurate prediction by averaging out the individual tree predictions. Think of it like getting more opinions before making a decision. More trees, more power. I can limit how deep each tree grows. This might stop it from getting too complicated and overfitting to my training data. It's like pruning a tree to keep it healthy. I can require more data points for each split in my decision tree to make it more general and less likely to overfit. Less overfitting means more stability, which is good news. I can reduce the number of features each tree considers. This adds some randomness and could prevent overfitting, especially if some of the features aren't very useful. It's like focusing on the most important aspects of the problem, ignoring the less relevant ones. Let's talk about mean squared error, MSE. A high MSE means our random forest regressor isn't predicting house prices very well. The predictions are far from the actual prices. We need to improve the model's accuracy. I'm increasing the number of trees in the random forest. More trees usually lead to better predictions because we're averaging out the results of many individual trees, making the model more stable and less sensitive to the quirks of any single tree. Think of it like getting opinions from more experts. The overall decision becomes more reliable. Here, I'm reducing the maximum depth of each tree. A shallower tree is simpler and less likely to overfit the training data. Overfitting means the model learns the training data too well, and it doesn't generalize well to new, unseen data. It's like memorizing the answers to a test instead of truly understanding the material. You'll do poorly on a new test. I'm increasing the minimum number of samples required to split a node in a tree. This creates simpler trees, again reducing the risk of overfitting. Think of it as being more careful about making decisions. We require more evidence before making a split. This one's about reducing the number of features each tree can use during training. It introduces more randomness and helps to prevent overfitting by making the trees less sensitive to individual, potentially noisy or irrelevant features. It's like asking several experts to make predictions based on a limited set of facts rather than everything available, reducing the risk of them focusing on less important details. I see that. RandomForestRegressor uses many decision trees. Increasing the number of trees generally makes the model more accurate and less prone to errors caused by just one tree being wrong. Think of it like having more opinions before making a decision. You'll likely get a better outcome. This reduces variance, meaning the results are more consistent across different datasets. It's a good first step when you're trying to improve a random forest regressor. This parameter controls how many features each decision tree can consider at each split. If you reduce this number, you add more randomness to each tree's decisions. This can actually help prevent overfitting. Situations where the model learns the training data too well but doesn't generalize well to new, unseen data. This one's straightforward. It specifies the minimum number of data points needed to split a node in a decision tree. Increasing this value results in simpler trees. Simpler trees are less prone to overfitting, meaning they generalize better to new data. Think of it as making sure each branch decision is well supported by enough evidence. I think of this as the height of a decision tree. A lower max depth creates a shallower, simpler tree. Simpler trees are less likely to overfit, since they won't learn too many intricate details from the training data. It's a way to control model complexity and avoid picking up on noise in your data that won't generalize to unseen data. MSE, or mean squared error, is a metric that tells us how far off our model's predictions are from the actual values, on average. A high MSE tells us that our model isn't doing a very good job at predicting the house prices. It means our predictions are quite inaccurate. Variance refers to how much the model's predictions change depending on the training data. High variance means that the model is very sensitive to small changes in the data, leading to inconsistent predictions. By reducing variance, we get more stable and reliable predictions. Overfitting happens when your model learns the training data too well, including noise and irrelevant details. This makes the model perform poorly on new, unseen data. We want a model that generalizes well, not one that just memorizes the training set. The techniques mentioned help to avoid this problem, resulting in a more robust model. This is the same concept explained above, but now we're looking at how it affects the model's performance. We aim to build a model that performs well not just on the training data, but on new and unseen data. This can be achieved by simplifying the model complexity, as explained earlier. This refers to the same concept of controlling the model's complexity to improve its generalizability to unseen data. By adjusting parameters that affect model complexity, we can avoid overfitting, making it more robust in making accurate predictions on new data.